Okay, so let's go back to Faraday's law. In Faraday's law, if you guys recall, we said that the equation is basically electromotive force, all right? Electromotive force equal to minus n d phi b over dt, all right? So the time variation of the magnetic field is represented in the time variation of the magnetic flux, and this gives electromotive force, okay? But what is this electromotive force? When we try to apply it to a loop, okay, this electromotive force is basically for example, in this exercise here, generates a current I, okay, over a loop. You can see that this goes like this, like that, like this, like that, okay. So that's my loop, all right? So this electromotive force E is a battery, what you call motion electromotive force. I just remind you that the electromotive force has nothing to do with the force, but it's basically a battery, okay? Or more precisely, a potential difference, okay? So E is a potential difference between 2 points, okay? And this, and the current, the resultant current is in a loop, okay? Which you can see is no, Bilal, I will come back. I will redo what I did before recording. Okay, so this electromotive force generates a current in a loop. Okay, just remember this point. So basically now, these electrons are making a loop, right? So they are circulating. In this case, counterclockwise, because the V is to the right, is moving the right, V to the right, and consequently, the electric field which is generated in also in a loop, right? It's also in a loop, which is in the opposite direction as the current. So consequently, when we write Faraday's law in a slightly different form, this is Lenz's law. Okay. In this case, in this case, I'm integrating. So my delta V between 2 points, is an integration over the loop that the electrons are doing. Okay, and it can be between 2 points, but it can also between the other points. So once again, so this loop. So for example, if I take this, this loop will be this loop here. Okay, or that loop here. Okay, so the time variation of the magnetic flux gives you electromotive force, okay, gives you a current, and also gives you electric field in a loop, okay, which will take place, which will generate a current in a loop. This is the reason why here it's said that it's an integration of a loop over a given loop. Okay, that's the reason why we have the Faraday's law written in terms of electric field generated in a loop. We have discussed all these before, and we have discussed this generation of. Let me just remind you of this equation here. I hope that you guys all can see it. Actually, you know what? I'm going to control X. I'm going to put it here. This one, just in case, because I like this representation. This representation really sum it all. Okay. Why it's not moving. Anyways, so as I said, the generation of a magnetic field, according to Ampere-Maxwell law, is written as dq over dt. That's the general. I would remember it like this, and this dq over dt is basically either the real current or obtained by Gauss's law as the time variation of the electric flux. So let's go back to the electromotive force here. I'm going to share a different So let me repeat for those who just joined us that we have seen Gauss law for electricity, where we have charge and electric field. We have seen Gauss law for magnetism, and that this reflects the lack of monopoles. Okay, and consequently, for any arbitrary closed surface that we choose, the electric field lines which are going outside this surface is exactly the field line going inside the surface. And Ampere's Maxwell law that I just mentioned is that integral of an Amperian of BDS is equal to mu 0 dq over dt, and this dq over dt is basically can be put in terms of, let me see. Okay, can be put as function of the induced current or the time variation electric field, which is represented by the electric flux. Okay, finally, I just discussed here that it's integration. Remember, when you have this sign, the integration sign plus this circle here, this means it's over a loop. Okay, so this is over a loop of the electric field, but usually this field is perpendicular to the flux. Okay, let me show you again. Let me show you again. This guy here. So this is the Ampere Maxwell. So again, if we go to here, okay, if this is my magnetic field is into the page, my bar is moving to the right, so my magnetic flux, okay, is changing. And now notice what is the current direction. The current direction is perpendicular to the magnetic field. So because it's in the plane, okay, and the magnetic field is into the page, and the induced magnetic field is up the page, okay. So this electric field, this loop shown here. Let me show it here. Actually, this loop here is perpendicular to the main magnetic field or the main magnetic flux which is changing. Is this clear, guys? I repeat. I'm going to repeat. Okay. So let's consider this case here, where I have a bar moving to the right. I have a bar and it's a magnetic field. I have some resistance on. This bar is moving to the right. This gives me a changing in the magnetic flux. This change in the magnetic flux gives me the E, which is shown here. That's my okay. This electromotive force E gives me a current, which is circulating here counterclockwise. Okay. The reason why it's counterclockwise is that because my flux is increasing, Lenz's law tells me it's going to oppose the change. So the induced magnetic field should oppose the external magnetic field. Consequently, it's going to be up the page. And since B induced is up the page, then my current is going to be in this direction. But the other property that probably I failed to mention earlier is that the circulation of I is perpendicular to B. And thus it's perpendicular to B induced, okay, by the right-hand rule, and thus it's perpendicular to B external. Consequently, this loop here is not a completely arbitrary loop. It's a loop which is perpendicular to the magnetic field. Okay. It's a bit. I don't know if it's easy for you guys, but I think that I repeated 3 times. So in the other case, when the bar was moving to the left, in this case, my magnetic field is decreasing. Lenz's law tends to oppose the change, so induced magnetic field is into the page. Is into the page, and my current is now clockwise. But now I want you to focus not whether it's clockwise and counterclockwise, but on the fact that this loop is perpendicular to B. In both cases, it's perpendicular to the magnetic field. Whether the bar was moving to the right or moving to the left is perpendicular to, so the current I is perpendicular to the magnetic field. The current I is perpendicular to the magnetic field, thus the electric field is also perpendicular to the magnetic field. Okay? You have questions on that? Okay, that's all. Okay, so let's go back to our beloved Faraday's law here. So basically, in a summary, what James Clerk Maxwell did, he actually took these four equations. I remind you that Gauss is a German Swiss. He lived in Germany. Ampère is a French. He lived in Paris. And Faraday, who was the teacher of Maxwell, he lived in Cambridge, in the UK, I think in Cambridge. Maxwell is a Scottish scientist who had the idea to put these four equations together and to form what we call now the Maxwell's equation. Okay. He added another equation. I'm not gonna do that. I'm gonna skip it. This is what we call the conservation of charges, but it's okay. I would like to remind you, before I continue to the Maxwell equations, that if I have a charged particle, okay, which is in an electric field and a magnetic field, the general force which acts on this particle is called the Lorentz force, and it's equal to the charge Q multiplied by E plus V cross B. Of course, I think that you have recognized that QE is the electrostatic force and QV cross B is the magnetic force caused by the magnetic force, the magnetic field, as well as charge in motion. Because in this case, V is the initial velocity of the charge, okay? So what this equation tells you, if my V is equal to 0, then the electric field will lead to acceleration. And now if V different from 0, then I'm going to have a magnetic force which is going to change the direction of my particle motion. Okay. Also remind you that if the motion of the velocity is parallel to the magnetic field, then V cross B is equal to 0, and it will not act on the motion. Then the magnetic field will not act to change the velocity of the motion of the particle in motion. So we have these four equations, okay? So Maxwell equations together with the Lorentz form the foundation of classical electrodynamics, classical optics, and electric circuits. The reason why this lecture is very important is that usually physics 11 is given in parallel with circuits. Usually students, they have the impression that we are mostly dealing with circuits. So if I put a capacitor, inductor, resistance, and then we play with it. Actually, what I would like to say here is that the one important consequence is that, so what these equations actually turns out that they deal with the with electromagnetic radiation. Okay, so the same laws of physics which are used and you guys will be using to solve electric circuits are the laws which are used to solve electromagnetic radiation. Okay, and this was said by our friend Mr. Maxwell. Okay, to give you an idea, and here I want you to bear with me, the mathematics is going to be slightly different from what we have seen, but it's interesting and of course not required in the it's not required in the exam, but it gives you an idea, an interesting idea, because I think that most of you have heard that the speed of light is a universal constant. Okay. But why? Where does this come from? Okay. Well, actually, the speed of light was actually calculated by Einstein. Okay, and it was calculated using Maxwell equations. And furthermore, I already explained that since the particle motion generates a magnetic field, consequently, this motion is relative to a reference. Okay, and this really is like a window towards relativity. So whether I have a magnetic field or not depend on the reference that I'm in, that things are relative. And this opened the door for relativity. Okay, so bear with me this wave graph here. All right, so let's see. Here now I probably have the capability of. So I'm going to use the Maxwell equations in their differential form and not in their integral form. Okay, I know that you don't know that, but certainly you know what divergence is. What's a rotational or a vectorial product of a derivative? Okay, and let's try to see what are the Maxwell equations. So I assume that I have a laser beam, and this laser beam is propagating in space. Okay, and I want to understand how this propagation is taking place. Okay, all right. Let us assume for a second that Maxwell equations that were developed by the various components, the various authors, is responsible for this radiation, for this propagation. In this case, I don't have a charge, right? It's just the laser. If I don't have a charge, then my rho is equal to 0. This means that I don't have any charge which are there. And also my J is equal to 0 because I don't have any electrons. It's just light, okay? Just the light which is going in space, okay? Consequently, I have my divergence of E I'm going to allow you to follow up one after the other. Okay, my divergence of E is equal to 0. Basically, this is saying that the Gauss's law, which is integral of EDS Q inside, I don't have Q inside. So the integration of a Gaussian surface is equal to 0. Okay, so this is first equation. Second equation, let me go to the third one actually, just to give divergence of B is equal to 0. We have discussed divergence of B, and I told you that Gauss's law for magnetism, for this course, it is required both the integral form and the differential form. So the integral of BDS is equal to 0, which is divergence of B is equal to 0. The same thing. Okay? That's the integral form and the differential form. All right. Now let's go to our friend Mr. Let's say Mr. Ampere. What did we say with Ampere? In this case, once again, we have light going in one direction. I don't have current. I don't have electron flowing. Okay. So what I'm going to do, I'm going to use dq over dt is equal to d phi e over dt. Okay. So in this case, I'm using id. In is equal to 0. And the I displacement is different from 0 because I have a time variation of my electric field. Okay. It's time variation. So in this case, I can write my Ampere-Maxwell law to be the one in red, which is written now. Rotation of B is equal to epsilon 0 mu 0 dE over dt. Once again, that's the differential form for Ampere's law, which is shown here. Integral of an Amperian loop of B scalar ds is equal to mu 0 I inside plus I displacement. I inside is equal to 0 because I don't have electron moving. I displacement is equal to the electric field. Okay, we have seen that here. No, we have seen it in the other course. So it's equal to B. Okay, and now finally we go to our friend Mr. Faraday. This is our friend Mr. Faraday, and that is the magnetic field. The time derivative of the magnetic field is equal to the rotation of E. This is coming from this equation here. d phi b over dt gives you dB over dt. And this integration will give you the rotational of the electric field. So we have now these 4 equations, okay? And I only have basically two unknowns, which is the electric field and the magnetic field. So that's great, because now I can try to solve these equations, okay, to get the conditions for this propagation, okay? So what we do usually, okay, is that we take some mathematical calculations. So we take the rotational. Once again, I don't require this, just follow with me. It's not required, okay? And I use this one, and I apply the rotational of this equation here. So it's going to be rod of E equal to minus d over dt rod of B. But rod of B, I have it here, which is equal to epsilon 0 mu 0 dE over dt. So what do I have? I'm going to have rod of E equal, which is equal to this one, and equal to this one because divergence of E is equal to 0. Okay, blah, blah, blah. And so at the end, we come back to this equation here. At the end, one can show that these equations can be put either this equation, if I choose to eliminate the magnetic field, or that equation if I choose to eliminate the electric field. So once again, I start with Maxwell equations. We take rho and j equal to 0. I don't have a source, so basically because I'm studying electromagnetic waves, I don't have electrons. Okay, it's just photons, mass equal to 0. And then now I try to get the equation that describes this motion, okay, assuming that the electric field is time and space dependent, because of course it propagates as a function of time. If you have a laser, this laser is shining and the electric field and magnetic field are propagating as a function of time, okay, and that's the only thing that I'm going to assume. All right, and so now these equations are well-known equations in mathematics, and they are called the wave equation. So basically, what Einstein found, is that the solution for these equations is simple sine waves. Okay, if you replace sine of omega of kx minus omega t, okay, okay. If I have these equations in mathematics, they are rather simple. It's like a pendulum equation or something like that, okay, where I'm going to have the solution will take this form. For example, if you assume only in one direction, so we have d2e over dx squared equal to epsilon 0 mu 0 d2e over d t squared, or the same thing for the magnetic field. Now you can see that this is a wave equation such that it's going to propagate at a velocity equal to 1 over square root of epsilon 0 mu 0. And that is your speed of light. That is where the form of the speed of light comes from. Okay? And this is, of course, this is huge, right? Because we start with something about electric field, magnetic field, charges, and now we are able of determining the form of my speed of light. Okay, if you put the constant epsilon 0 and mu 0, which were determined, then you get now immediately the speed of light, which is 2.99 10 to the power 8 meters per second. So what I'm trying to say is that, and we will come back to the form of the electric field and the exact form of the solution. Okay, and what we can say is that the solution of this can have the form E equal to E0 sine of kx minus omega t. That's the general form for this equation here. We'll come back to that in a few seconds. Okay, but for the moment, I just want to make sure that that we have the form, at least, of where does this speed of light come from. Okay, and so this is BAE, but also the same thing for B, because B has the exact same form. Okay. Okay? Do you have questions?
سر مش it's B محل E يعني B equal
Sorry,
B0
yeah, sorry,
sine
B,
KX.
exactly, B. Thank you. Are you guys following what I'm trying to do here? Hello? Leah, can you unmute and answer? Or reply on chat? I just want to see if you guys are with me or just put this thing and then. Yes, yes. Leah, yes, you. Are you following?
Yes, sir. Everything's good.
Vera, are you following? May? Tamar?
Yes.
Noor?
Yes, I'm following.
Did you guys understand what we're doing here? That what we have done.
Yes.
Did you follow up loosely? Once again, this is not required from you, okay? This is not required from you, but I thought that it was really an interesting, simple, relatively simple, of course, calculation, but with a huge consequence. And that is the form, what is the speed of light? Okay, and now I hope that you guys are a bit more, let's say, convinced that these equations, which are maximum equations, they concern electromagnetic waves. Okay, so let me continue a little bit. Do you have any questions so far? Definitely, we can come back to this whole thing. Right?
Sir, the meeting will cut off in less than a minute.
Yes, yes, I will. Yes, let it cut off, and then I'll reconvene. Okay. Less than 1 minute. Yes. So I'm gonna wait. I'm gonna stop recording. Just give me a second.